Welcome, physics, to another flipped lecture. We are talking about light and reflection today. We're in chapter 23, and we are moving into our optics unit, the last unit that we will get to in academic 2015-2016. We are in the final stretch. Keep working hard, and you'll see the tape soon. All right, here we go. Chapter 23, light. You've met light before. Light is a form of the electromagnetic spectrum. It's part of the energy of the electromagnetic spectrum, along with others like X-rays and radio waves and microwaves and things of that nature. You've met this before in physical science. You also talk about it in elementary school as well. So these are concepts that you should be very familiar with. If you need review on what the electromagnetic spectrum is, what electromagnetic energy is, then you need to get that on your own. We're not going to focus on that part of the chapter here in the lecture. After moving through a brief introduction of the electromagnetic spectrum, chapter 23 deals with sources of light. So this as well is covered in physical science, but we will stop here for a moment and make sure that you understand the concept. So light can be created by heat. Whenever something has temperature, it glows in the infrared spectrum. And the hotter it is, the brighter it glows, and the shorter the wavelength of light that it produces. So the glow from an object, because of its temperature, is usually not visible by us because the eyes that God gave us can't see infrared light. But when something gets hot enough, that light starts to be emitted in the visible spectrum. And then we can see it. And so that's an incandescent source of light. Things like old school light bulbs, incandescent light bulbs, they glow really hot, and that turns into light that we can see. Okay. Also, if you stick a piece of metal in the fire, it gets red hot. That's that same idea. The more thermal energy that's present, the brighter it is, and the higher the frequency of light. Another form of light production is a gas discharge tube or a fluorescent light bulb. And in here, it doesn't have anything to do with temperature. Here you're exciting the molecules of a gas by some other form of EM radiation. So an X-ray hits it, or an electron hits it, or something of that nature, and the electrons of the gas move to the next higher energy levels, and then they fall back down. And when they fall back down, they release a photon of light. So light is released according to the electron configuration signature of the element that you're exciting. And because of that, every gas that is used in a fluorescent tube has a different signature of light wavelengths that it produces. And so this is excitation and then relaxation, and it's the relaxation that emits the light. Okay? And so every element has a signature that is unique to it. Here's a little spectrum review for you. A radio wave is very, very long, something like 10 to the third meters long. And so there are, buildings that are measured in 10 to the third meters. Radio waves are very long things. Microwaves are shorter. Now we're looking at 10 to the negative second. So something like, something that you would measure in centimeters, like butterflies. The infrared has things in the order of 10 to the negative fifth meters of a wavelength. And so we're looking at the tip of a needle as an example of that kind of size. And then visible light has wavelengths in the 10 to the negative sixth meters. Microscopic organisms, protozoans, bacteria, things like that are about that size. Ultraviolet light has wavelengths around 10 to the negative 8 meters. Molecules are about that size. X-rays are 10 to the negative 10th meters, and individual atoms are about that size. And then gamma rays have wavelengths of 10 to the negative second, and that is somewhere around the size of an atomic nucleus. So these are just different ways to help you think about how long wavelengths are of these various kinds of energy. Okay? Light and reflection. There's other ways of forming light. We talked about incandescent light, and we talked about fluorescent light. Others would be light-emitting diodes. An LED, we use them all the time now in electronics. Initially, it was just a checkpoint in the circuit to see if electricity was flowing there. So an LED would light up like on a power button, and you'd say, hey, look, power there. But then they discovered that they can use these little circuit components that give off a small amount of monochromatic light, and they can miniaturize them and use them to make images. And so LED televisions are now being made. LEDs do all kinds of things in our world, and that's because of this little component called a light-emitting diode. And it emits light when electricity is present, and it consumes very little power. And it is monochromatic, and so it produces only one wavelength of light, so that's useful. We can use that in particular applications. And recently, they've been able to make LEDs that are very, very bright. Some of the brightest flashlights you can buy are not incandescent or fluorescent. They're LED flashlights, and they are ridiculously bright. Lasers is another form of light, and a laser is called coherent light. So it's monochromatic. It's all one color. It's all one wavelength. And it's in phase. So it rises and falls, all the waves rise and fall together. And I'll show you an image of that in a minute. And so all the peaks add, all the troughs add, and you have very, very high energy light that is produced, which is what allows them to be useful in lots of applications. We can cut with them, we can read with them, we can measure with them, do all kinds of different things with lasers. And then cold light is the last source of light. Cold light is something that is derived by a chemical reaction. Cold light would be an example that would be bioluminescence or chemoluminescence. Chemical luminescence would be like a glow stick. You crack the little glass tube and the two chemicals mix and it glows. Or like a firefly, or like red algae, or things of that nature that are alive and can produce light. And that is because of chemical reactions going on inside their body. And God was very creative in some of these things that he made. So here's examples of incandescent light. Here is obviously the sun is very hot and glowing. Light bulbs are hot and glow. Candles are hot and glow. Fluorescent tubes, fluorescent light bulbs, and various different kinds of gases in this tube. They all glow a different color because of the gases present in them. And again, remember, fluorescent light is created because electrons are excited and then drop back down to their home state. More versions of light bulbs. That back in the past we had incandescents. In the last, I don't know, 15 or so years we've had fluorescent, and now LED light bulbs are taking over the world. Here's LED flashlights, here's another LED light bulb, and LEDs are just going crazy because they use so little electricity. They help us conserve our energy resources, they help lower your power bill, and they also are really bright. And then, of course, lasers. Lasers are light that is coherent, meaning it's all one color, and it is all rising and falling together. The waves and the troughs add up. Okay, so we use lasers for lots of things. We use lasers for measuring distances, for reading CDs at concerts and things of that nature. And this is the original method of making a laser. We've gotten a little bit different now, but here we have a flash bulb wrapped around a ruby, and there's a mirror housing in the back. The flash bulb excites the ruby, and the ruby emits only one color of light when that happens. And so the one color of light comes shooting out the front, and because it's all being made in one instance, in one crystal, it's all coherently moving together, and it's all monochromatic. So we get this very high energy beam of light coming out. Okay. Of course, we are ways away from being able to use lasers like science fiction uses them. We could probably create a very high energy laser beam that you might be able to use to cut and kill, but the problem is it wouldn't only be a couple feet long. It would go on infinitely long, and it would kill everything in the universe, so that would be a problem. So lightsabers are still not real, but we're moving on. Here's an example of bioluminescence. This is red tide. It's a kind of algae that when disturbed, when shaken like it will in a wave, it glows. Really, really cool. We don't have that very much here in Hawaii, But other places with colder water tend to get these algal blooms that glow. It's really cool to see at night. So that's an example of bioluminescence. The speed of light has been measured very, very accurately. Starting back in the 50s, 1950s, people started to get a good handle on how fast light was traveling, and our precision has gotten a lot better. And now, so the actual speed of light is this number here, and we round it off to 3.00 times 10 to the 8th. That's our common expression here, meters per second. If you wanted to think of how fast that is, 3 times 10 to the 8 meters per second. A photon of light, if it were in a circular track, could lap the Earth 7.5 times a second. So 1, 1,000, 2, 1,000, 3, 1,000, 7.5 laps around the globe every second. That's pretty stinking fast. But it still is, it takes 9 minutes to travel to the sun. So we're about 9 light minutes away from the sun. And it would take, at that speed, 4.24 years to get to the nearest star, Proxima Centauri. So the universe is a big place. God is a big God. Light can simultaneously be seen as a particle and as a wave. So when we think about its nature, it reflects and refracts and diffracts like a wave. But it does come in discrete quantities. We can talk about the quantum of light, about how much light got somewhere. And when we analyze how much light we might have, there's always, it's chunky. It doesn't come in smooth increments. It comes in discrete quantities, units. So think about the difference between like pouring sugar out of a bag of sugar or pouring sugar out of a bag that had sugar cubes in it. The sugar cubes come in chunks. They come in discrete quantities, and you can't have half a sugar cube. Light is like sugar cubes, not like a bag of sugar, right? It's not smooth, it's chunky. And so because of that, it does have a particle nature, but it also behaves like a light wave. And so we have had wars in physics about is it a particle or is it a wave? And just some of the examples here, when we analyze it, we can polarize it, and polarizing is something that happens to waves. Particles don't polarize. But we also look at the fact that we can measure light in a quantum. So it's weird. It's both a light wave and a light particle. If it were purely a particle, we would expect that light would go zipping past a barrier and we'd have a straight line shadow. But in fact, it waves and it bends, and shadows tend to do this kind of stuff. And so it's a wave and it's a particle. It's both. A solar panel only works because of the particle nature of light. Lenses only work because of the wave nature of light. So again, it's a unique kind of thing. So there's this, light is a particle. Light's a wave. It's a particle wave, particle wave. Checkers, let's stop this petty bickering and resolve our debate like professional scientists. Okay, Sasha, and then fine. Physicists have been arguing over this for a long time. So it's both light and a wave and a particle. When we study light, we always simplify it, which physics does for lots of things, so that we can imagine where light is going. And just like in hydrodynamics and liquids, we imagined things called streamlines that don't actually exist. Here we imagine things called rays, which don't actually exist, at least not the way that we draw them. So a ray is an imaginary straight line pathway that light takes. It helps us analyze the action of light on a mirror or the action of light in a lens. And so when light strikes a reflective surface, it bounces off in a different direction. We call that reflection, and it will form a virtual image. The light hits the mirror, bounces off the mirror, and we, observing that, think we see the object behind the mirror. It looks like it's behind the mirror. That this morning when you were doing your hair and brushing your teeth, and I hope you did that. I probably didn't do my hair, but when you were brushing your teeth and doing your hair, because you have more hair than I do, you saw yourself. but you didn't see yourself in front of the mirror. It looked like you were standing behind the mirror, right? And that is called a virtual image. Virtual images are images that look like they're somewhere else. They look like they're not where they actually are. Mirrors create virtual images. And when we measure how a light ray bounces off of a mirror, we create something called a normal line, and that's a line perpendicular to the surface of the mirror. So mirror, normal line, perpendicular to it. You've already met that concept when it comes to a normal force. Way back in mechanics, a normal force is a reaction force that pushes up on an object in response to its weight pushing down, right? Now we have normal lines, perpendicular line to a reflective surface. And a light ray coming in will make the same angle with the normal when it strikes the mirror as when it leaves the mirror. So we'll say that theta reflection equals theta incident, that the light coming in strikes the mirror at the same angle to the normal as the light leaving. So look at this background. Here's a light ray coming in, and it strikes a reflective surface and it goes off this way. And if we were to measure from a perpendicular line, hard to draw a perpendicular line, but if you had a perpendicular line here, the angle that was formed here would be the same as the angle that's formed here, right? Theta reflection equals theta incident. Here's another diagram of that. The incident ray comes in, here's a mirror, here's my normal line. The angle of incidence equals the angle of reflection. So it bounces off and is the same angle on both sides. Here's a little picture to help you think about a virtual image. You are looking at yourself in a mirror, right? And the light rays from your feet are coming up and hitting the mirror and bouncing off the mirror to strike your eye. But this ray coming off of the mirror and striking your eye, it looks to you as if that line keeps going backwards and that your feet are actually here. Kind of cool. And the image of your face comes off, well, the top of your head comes off the top of your head, hits the mirror, comes back and strikes your eye, and it looks like that ray is actually coming from back here. And so you look like you are a ways behind the mirror. And if it's a flat mirror, you look like you're just as far behind the mirror as in fact you are in front of the mirror. And so that's a virtual image because you are not actually standing behind the mirror. Hope that's not news to you. Alrighty. Concave mirrors are mirrors that have that are like this. Wait, there you go. Concave means it goes in. Convex means it comes out, right? So a concave mirror is basically part of a sphere. That's the way that we will think about it. They're spherical mirrors with some distance to a center C. That distance is measured as a radius. We'll use R for that. And they tend to have fuzzy images because not all the light rays are focused to the same focal point. If you have a truly spherical mirror, the image is a little wonky. It doesn't quite look right. But we use parabolic mirrors to focus light. And if you have a parabola instead of a sphere, you get very, very good images. Some things to keep in mind when you're playing with parabolic mirrors is that any light rays that come in parallel to the optical axis are reflected through the focal point. That'll make sense in a minute when you see a picture. Light rays that come in straight are all reflected by the parabola through one point we call the focal point or the focus. Incident rays that pass through the principal focus are reflected parallel to the optical axis, so just the exact opposite. If a light ray comes through the focus and strikes the mirror, it's going to wind up leaving parallel to the axis. Again, you'll see a picture in just a moment. And incident rays that pass through the center of the curvature are reflected back through that same center of curvature. So if a light ray happens to pass through the center, then it'll reflect straight off of the mirror and go right back through the center. So let me show you some pictures for this. Here is a parabolic mirror. Here's the focal point. Here's the center. This is the axis. And this is a parabolic mirror, okay? So light rays that come in parallel to the optical axis, so straight at the mirror, are all reflected by the parabola to the focal point. Opposite, If you have a light ray that passes through the focal point and strikes the mirror, it's going to leave going parallel to the optical axis. Okay, it's the same principle. And any light ray that goes through the center will reflect back through the center. So that's not drawn here, but if you had a light ray that went like this and struck through the center and then hit, it would come straight back off and go right back out the center. Okay, you'll get to play with this a lot, so don't stress about it. Here's an example of an object that's being reflected by this concave mirror. And if we follow the light rays from the tip of the pencil, some of them go parallel to the optical axis, strike the mirror, go through the focal point, and would wind up going here. So the tip of the pencil image is flying around this way. Other light rays leaving the tip of the pencil might go through the focal point, hit the mirror, and then come parallel to the optical axis. So where those two line up, we would see the tip of the pencil. Okay? You could also go from the tip of the pencil through the center and see that it would reflect off the mirror and come right back, and we would, again, tip of the pencil image is right here. So you can draw these kinds of lines and help you discover where the image winds up. You have a pencil here, the image looks like it's here. That's where the pencil would appear. Okay, so we use round mirrors like this for magnification, for all kinds of things. To calculate magnification, you need the height of the image and the distance of the image, and the height of the object and the distance of the object from the mirror. Okay, and so we use this relationship to calculate magnification. Magnification is the absolute value of the height of the image divided by the height of the object. And so when you have these two items, you can determine if it's a larger image or a smaller image, if the magnification is positive or negative. I'm sorry, greater than 1 or less than 1. Convex mirrors always have a virtual erect image that seems smaller than the object. That's the sticky outie mirror, right? If the mirror comes to you, then the image will always be virtual. It'll be behind the mirror, and it'll always be erect. It'll always be standing up, and it will always look smaller than the actual object. So concave and convex mirrors. Alrighty, here's an example of a soldier and a round mirror here, a concave mirror. The soldier looks smaller and upside down if you were to trace all of the places that these light rays go. But if you put him in front of a convex mirror, he will look right side up, standing behind it, and tiny. And then this didn't populate correctly, but we use funny mirrors all the time to play with expressions that you see in carnivals and things like that. And that's it. If you have any questions, let me know, and we'll see each other tomorrow. God bless you.